Hey everybody. So today we're going to be talking about graphs of rational functions. What you will start to notice about this section is that the section is very much aligned with the stuff we learned in the previous section. It's just, unfortunately, they ask a lot of information. There's going to be quite a number of problems on the homework that have, well, these 12 parts to them. And so many parts, I can't even fit them on the board immediately. So let's just go ahead and get started, and I'll explain what I'm referring to. So we start off with a rational function. Again, this is a section on graphs of rational functions, so expect all of these functions to be a polynomial divided by a polynomial, as we talked about previously. And so the goal of these problems, so the directions technically say find a whole list of characteristics about the rational function so that we can graph it at the end. And so we start off by looking for, well, they're asking for the fully factored form of a rational. And we haven't really talked about the factored form of a rational, but really the factored form of a rational is just the factored form of the polynomials in the top and the bottom, in the numerator and the denominator. So they are virtually asking us to factor the numerator and the denominator as much as possible, if we need to. You may notice in this problem here, everything's factored for us. So there's even an answer choice in the homework that says it's already factored. So here for the factored form, it's already factored. So there is an answer choice for that option. And now we move on to the domain. And the domain, what that refers to is the values of x such that, well, we're looking for the values of x that make the denominator equal to 0. So remember, the domain, we set the denominator not equal to 0, so notice there is a not equal to sign. You will notice some of the answer choices will have greater than, less than. None of those matter in this regard. We're only going to be using not equal to. And in particular, what we're not equal to is precisely when the denominator is set not equal to 0. So the denominator, it's x times x plus 11. Let me try a different marker. So x times x plus 11 is now set not equal to 0. And because it's already in a factored form, that's how we get the two values of x that the domain is restricting. In particular, we get 0 and we get negative 11. And this would be your answer for this part. So far it starts off very tame, and we move on. Again, it's asking for something that we haven't seen the terminology for before. It's lowest terms. Now, it's not going to make sense in this context, but lowest terms means if there's anything to cancel after you factor, it wants the part after all of that cancellation. Again, it doesn't make sense here because, well, there's nothing that cancels, but there are problems that I will discuss that do have a cancellation. But for the time being, for the lowest terms, we're just going to say that, well, it's already in lowest terms, and there is an option for that. So we will conclude already in lowest terms. Again, we'll see other problems that don't have this conclusion. We actually have to apply one additional step. Now we move on to the x and the y-intercepts. So keep in mind, the x-intercepts are also the zeros. Remember that terminology from before? I mean, we still find it the same way. To find an x-intercept, you set y equal to 0 and you solve for x. So another way you can think about this is the x-intercept of a rational function is when the numerator is set equal to 0. And so the reason that happens, so you don't have to know that, but if you like shortcuts, that is a shortcut I'm providing. So for the x-intercept, so here's the scratch work. So we set y equal to 0, and we're solving for x. And so what we get from this is, remember, the rational function's all the way up there. We set the function equal to 0. And when you clear out the denominator to get, well, when we clear out the denominator, which is something we're typically used to doing, notice the denominator times 0, whether you use cross multiplication, LCD, you will just get that the numerator is equal to 0. And that is why, and that will happen for every rational function. So you can think about the x-intercept throughout this whole section. Yes, this whole section. The x-intercept is just when the numerator is set equal to 0, and you solve for x. So from here, what we get is, well, as I just said, the numerator is set equal to 0. And we conclude that x is negative 8. So x is negative 8. And you can leave the answer just like this. In the notes I even say, write down an integer or a simplified fraction, so this would suffice. So, furthermore, the y-intercepts. Remember, the y-intercept, this one's normally the easier one, because this implies we set x equal to 0, and we solve for y. So let's go ahead and do that. If we set x equal to 0, well, what simply happens is that every x is now set equal to 0. So now 0 plus 8 instead of x plus 8 divided by 0 times 0 plus 11. And something you may notice, if you put all of this in your calculator, then what's going to happen is you will get a domain error. It'll say divide by 0 error, provided you type it in correctly. And so what you conclude from that is that you can't get any answers from that process, which means a y-intercept does not exist. So here we get does not exist for the y-intercept because we would end up dividing by 0, and that can't happen, of course. So your conclusion for the y-intercept is does not exist. Try to space this out a little bit. And as I mentioned, there are 12 parts to this problem, and it looks like we're only a third of the way done, so bear with me. And so we move on to this idea of behavior at the x-intercepts. Whether there's one or a bunch of them, no matter how many x-intercepts we have, we're going to figure out something called its behavior. And what this behavior comes from, so if anything, let's list the x-intercepts. Let's just remind ourselves of what they are. We already found them. So it's x is equal to negative 8. So in particular, at x equals negative 8, let me remind myself of how the answer is formatted. And so there's a few things we have to consider in the sequence of steps here. What we need to do to figure out behavior, and we've done this before. Remember the word multiplicity? Well, it's coming back. And the multiplicity will tell us about crossing and touching, which will then help us choose an answer for this. Because as you will notice for this part, you will have a few answer choices, and some will say cross, some will say touch, and that's what we're determining here. So we cannot figure out crossing or touching without knowing the multiplicity. So at x is equal to -8, the multiplicity is, so for any function, the multiplicity comes from the factor that we got the number from. So x is equal to -8. That came from the factor of x plus 8. So it did come from that factor. Notice x is a factor, x plus 11 is a factor, x plus 8 is also a factor. And as such, what is the exponent of x plus 8? Well, you might think it's just 1. Of course, it is 1. And in fact, that's a good thing to identify. And in fact, it's 1, but even more specifically, the multiplicity is 1, which is an odd number. So it is an odd number. And since the multiplicity is odd, we have crossing. So the conclusion is it crosses at x is equal to -8. And there is an answer choice that will look very much like this part boxed in. Some will have the characteristic of touching. You want to go with the one that most closely aligns with this conclusion. And so we move on to the vertical asymptotes, which is actually something we found in the previous section. So remember, I mentioned that the vertical asymptotes are very much associated with the domain restrictions. So we found 2 domain restrictions, 0 and -11. Well, guess what? They're going to pop up again immediately here. And in the directions, I say type the equations from leftmost to rightmost, which just means put the smallest domain restriction first and then the largest one. So what number is smaller, -11 or 0? Well, -11, so that one goes first. And I do say type equations. So here the answer would be x is equal to -11, comma, x is equal to 0. And in your homework, it will be constructed as the leftmost asymptote is, and you would put this one, and then it'll have another blank. The rightmost 0, or rather, the rightmost vertical asymptote is, then you put this one. So just to give you an idea. And so we move on to part G, which says it wants to know the behavior at the vertical asymptotes. So we already did a behavior type problem up here. So what did we do for that one? We fooled around with the multiplicities of the factors. We're going to do the same exact thing here. It's just referencing different numbers. So what we're going to do, well, there's 2 vertical asymptotes. We're going to look at one at a time. We'll start off with x is equal to -11. At x is equal to -11, so we have to remind ourselves, what's the multiplicity of this x value? So we move on to finding the multiplicity, and the multiplicity will end up being, well, the factor that -11 comes from is x plus 11. That is the factor for which that number comes from. And we ask ourselves, what's the exponent of that? The exponent, or the multiplicity, is 1. So it's the same idea as before. And 1 is an odd number, which means we get a crossing interaction. But the only problem, so you might notice, none of your answer choices are going to say crosses or touches. They're going to say something about both sides of the asymptote go towards infinity, both sides go towards negative infinity, and one side goes one way and the other side goes the other way. So what does that mean exactly? Well, asymptotes are not x-intercepts. So there's no x-axis for which a graph will come touch or cross through. Instead, for asymptotes, what crossing represents is this alternation. So if on one side of the asymptote, the graph is going towards positive infinity, then what crosses generalizes to is that the other side has to go in the opposite direction. So one side will go towards positive infinity, the other side's going towards negative infinity. They must alternate. That's what the generalization is here. If I were to scratch out crosses and put touches, then if one side went to positive infinity, the other side also goes towards positive infinity. There's no alternation there. It does not, the infinity of the asymptote does not alternate. So here, the best way I could try to describe this implies one side goes to infinity, one goes towards negative infinity. Let me make sure you can all see that. Yeah, okay, so it's still on camera focus, good. And so that's the conclusion there, and that's only for one of the vertical asymptotes. We still have a whole nother vertical asymptote, which is x is 0. And it turns out x is 0, all this logic still applies. So I'm out of room and I'm not going to write it, but the x is equal to 0 part, it's the same exact conclusion, except this, you just replace this part right here with x is equal to 0. And that's the only difference there. So I will let all of you write that down, and I'll move on to, as I mentioned, there's 12 parts, so I'm going to move on to part H. So part H is asking about the horizontal asymptote. And this is actually something we found in the previous section. And this is where the degree of the numerator and the degree of the denominator have to be compared. And depending on their magnitudes, so the degree of the numerator being larger or being smaller than the degree of the denominator, that will tell us what the horizontal asymptote will end up being. So here, so the degree of the numerator well, the numerator's highest exponent is 1. The degree of the denominator, so the degree of the denominator is not going to be 1 because this is all factored, which means that you have to think about the term domination stuff that we mentioned in the previous section. So if you think about x times x plus 11, the term domination here, well, we have a factor here, and the term that dominates is just x. So notice x plus 11 now reduces to x because this x right here dominates that 11. Which means that the leading term is x squared, and that tells us that the degree is 2. So again, notice that 2 does not show up anywhere in this function, which is why term domination is so important. But since we have that the degree of the denominator is larger, since we have that this is larger, then what we can conclude is that, well, if you look back to the previous section, this always determines that y is equal to 0. That is the vertical asymptote. And so that's what I will write down here as the answer. That is the answer for the vertical asymptote. And as we move on to the oblique asymptote, so you might notice in my notes that I put the oblique asymptote and I filled in the blank. I put doesn't exist. So if you get to that problem, we're not going to have any oblique asymptote problems in this section. So I figured don't rack your brain over it. There's no oblique asymptote problems. If you see an oblique asymptote part, just put doesn't exist. I'm just giving you that one for free. So part I, I'm going to skip over and move on to part J. So skipping part I, move on to part J. So part J says determine the points for which the horizontal asymptote, again we're going to ignore the oblique asymptote, for which the graph intersects the horizontal asymptote. So the horizontal asymptote we just found. So what it tells us is if y is equal to 0, the horizontal asymptote what is x? That's all it's asking for. And some of you might already seem to know the answer, because we did this before. We have actually done this already. And let's see, it was for the, oh yeah, the x-intercept. Yeah, we've done this for the x-intercept already. So this was the same directions. If you want to do it again, fine, but this is the same series of steps that we did for the x-intercept. You set y equal to 0 and solve for x. And for that one, we found that x is -8. And that's from part D of this problem. We already did that one. So we'll move on to part K. And notice I left a decent amount of space for part K, because the directions are, well, they're pretty elaborate, to say the least. Use the real zeros of the numerator and the denominator, blah, 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 determine stuff. Okay, so there's a lot going on there. But this part right here, part K, this will also show up in the next section. So you really need to pay attention to this part. This is probably the most important part of this whole problem, is part K. And so what I'm going to do is I'm going to just give you a step-by-step process for solving this. So the first step is to list. I just want you to list all of the x-intercepts and domain restrictions. So just list them all. And we have found all of these things already. So the domain restrictions we found in part B. So the domain restrictions we found in part B, those were 0 and -11. We also found an x-intercept. We found that in part D. So this was in part B. And then part D, we found negative 8. So that's the first step. Just list all of them. Just bring them back, just as a reminder. From there, what we want to do is we want to throw all of these on a number line. So this is part 1. Part 2. Put all numbers on a number line. Alright, so if you don't remember what a number line is, I'll write it out for you. So it's this thing, and we're going to put them in order. We're going to order these from smallest to largest. Negative 11 is the smallest, and then negative 8, and then 0. And so once we have all of these plotted, the next step here for part 3, in fact I'll give this a little bit of space, is we want to, I'll write down the direction after I apply it. The next direction though is we're going to pick numbers from each interval. So notice, whenever we plotted these 3 numbers on the number line, we broke the number line into 4 segments. Yes, 4 segments. This is a segment, that's a segment, that's a segment, and that's a segment. So each one of those segments needs to have a representative from it. So from this segment over here, the number that we're going to choose, so notice I'm using a different notation. This is called a test point. So I'm using a different notation for it to distinguish it from these values. From here, I just have to pick any number that lies in that segment. So virtually any number less than negative 11. I'll pick negative 12. Again, it doesn't matter, it's a test point. So negative 12 is 1, and then from this segment, I need a number that's greater than negative 11 and smaller than negative 8. So negative 9, negative 10, use negative 10. Again, it doesn't matter. This choice is, as long as you pick it in the correct interval, then you're fine. And then from this segment, I'll pick negative 1. Any number that's larger than negative 8 and smaller than 0, negative 1. You can pick negative 2 or negative 3, anything that lies in that interval. And here, any number that's just greater than 0, I can pick positive 1. So what we're doing is we're picking test points from each interval. So picking test points. And again, I'm using different notation because I definitely want you all to distinguish these from the values that we plotted. We'll see why in a bit. So once we have these test points, what we're going to do, so we're going to plug each test point into the original function. And what we want to do, once we do this, we want to determine whether the output is a negative number or a positive number. We don't care about the number itself, we just care about whether the number is positive or negative, and I'll show you what I mean. So the first number that we had was negative 12. So we plug in negative 12 into the function here. So notice I'm putting x is equal to negative 12, which implies, well, negative 12 plus 8 divided by negative 12 plus 11. And so what my normal suggestion is, I wouldn't recommend throwing all of this in the calculator at once. I would recommend doing the numerator first and then the denominator and bringing it all together at the end. And then Yeah, and then bring it all together at the end. So I did mention that all we care about is the sign of the number and not the actual number itself. So I'm going to look at this, and whatever number you get, you'll get a negative number. So I'm going to put a negative sign here. Again, we don't care about the quantity, we care about the sign of the quantity. So that's why I only care about the negative sign. Let me make sure you can all see that. Okay, cool. And so we do that, and after you do that, so notice, negative 12, it was a test point, which means we used it in one situation. Now that we used it, I'm coming over here to negative 12, and I'm scratching it out. Trust me on this. We use the test point, scratch it out. This will help you so much from my experience helping people with this. And so we do not touch negative 12 anymore after we get this corresponding sign. However, that sign that we got, it will go, so where did that arrow come from? Right here. So that sign that we got will now correspond to that segment. And I'll show you how this is relevant later on. So let's keep going. So negative 10 is next. So it's the same idea. I just so happen to know that we're going to get a positive number from that. And then negative 10 is gone. If you plug in negative 1, you're going to get a negative number. And if you plug in positive 1, you're going to get a positive number. And for this problem, this is one way to do it. Yeah, so as I mentioned, and hopefully everyone's on board with this, you plug in negative 10 into the original function, and you will get a positive number. If you plug in negative 1 into the original function, I just so happen to know that you're going to get a negative number from that. And that would scratch out the negative 1 over here and allow you to put that corresponding negative right where the negative 1 was coming from. And x is positive 1, that's the last thing. The reason why I'm able to figure these out so quickly comes from another method, which I decided to explain in the next problem, which is very similar to this problem. So, and you could just choose whichever one your favorite is. So we did all of this for step 4, just so we can fill out this number line. Oh yeah, and then positive 1 is gone. So we did all of that to fill out this. We have still yet to answer the problem. So we still need to reference this number line. So what we're gonna go ahead and do, I'll erase what we got here. And so now that we have this number line, now we can answer the question of determining where the graph is above the x-axis, which that would be represented by all the plus signs, and where the graph is below the x-axis, which is represented by the negative signs. So I guess we can call that step 5, because step 4 was the previous one. So we'll start off with above the x-axis, and this will come from any segment that has a plus, a positive number, because positive numbers are up above this axis right here. So above the x-axis, so which segments have plus signs? This segment right here, from negative 11 to negative 8, has a plus sign. So we want to denote that using interval notation. So it starts off at negative 11, it ends at negative 8, and that would be one of the segments. And you might notice, well, hey, there's another segment. And you're right, we're going to add that one in a bit. So we do not use a union The union's normally just for the domain, if we have to put it in interval notation. So here, and I think it even says separate with a comma, so I will use a comma to represent the other segment that has a plus sign. And that segment seems to be starting from 0 and going all the way to positive infinity. So this would be your answer for above the x-axis. And this whole process is something we'll do in the next section as well. So this part K that I have in the notes, this is very important here. And this also leads towards why I made you all scratch out the test points after you use them. I've noticed a lot of students have the test points as part of their answer. So instead of the 0, they would have, say, -1 to 1 or 1 to infinity or something like that. And that's kind of the reason why we have test points, is because they're temporary. Temporary points, we use them once and they disappear, never to be seen from again. So that's why I emphasize everyone to scratch these out. It's these values that your final answer will be based upon, not your test points. Your test points are used once and they're gone, which is why they're test points. But enough rambling, let's go ahead and look at below the x-axis. And this is just the contrary. This is just segments with a negative symbol. So this segment has a negative symbol. That segment seems to come from negative infinity all the way to -11. So negative infinity to -11. And we use a comma because there is in fact another segment. This segment starts at -8 and ends at 0. And so that concludes part K. But unfortunately, we're still not done because there's one more part that says use everything we found to determine the graph of the function. So let's go ahead and conclude with that. And fortunately for us, choosing the graph, my math lab has it set up as multiple choice. And half of the answers are going to be incorrect just right off the bat. I'll explain how you're able to determine that in a bit. So move on to part L. So really the only things that you need to identify from here are, well, your asymptotes and these characteristics right here. That will help you distinguish this graph from all the other ones. So let me motivate where this graph is coming from. So let's start off with the asymptotes. So the asymptotes, we found the vertical asymptotes in part F. We found 2 of them. It was -11 and 0. So at around -11, we do have an asymptote. And also, at x is equal to 0, it's a vertical asymptote. And vertical implies up and down. So we have an asymptote right here as well. So this is an asymptote at x is equal to -11. This is an asymptote at x is equal to 0. And we also have a horizontal asymptote that we found in part H. In part H, it said that the horizontal asymptote was y is equal to 0. Horizontal means left to right, so we will do just that. Now the reason why this already helps you narrow down the problem is because 2 of the options in this problem don't even have 2 vertical asymptotes. They only have 1 vertical asymptote. But of course that's impossible. We found 2 vertical asymptotes, so we can narrow down the choosing of the graph to just one of 2, and their only difference lies in what they consider above the x-axis and below the x-axis. So if anything, we can see where these segments start to come into play on the graph. So here it says that we are above the x-axis from -11 to -8. So here's -11, here's, let's see. Okay, so there is -8 was something we found to be the x-intercept. So x-intercepts are still into play. That would be about right here. So if anything, that does give us an idea of, well, more characteristics that are occurring. And I think the two remaining graphs will both have that x-intercept. So here we're above the x-axis from -11 to -8. So in particular, here's -11, so it's above the x-axis, and it's above all the way until -8. And as we can see, from -8 to 0, that's where it starts to go below. So that's why this goes below, and it starts to trace this side. Now this already will help you identify the final graph to choose from, because the other option will just have every segment flipped. But for completion, I'm just going to go ahead and fill in everything else and motivate where all of this is coming from. We also have, so we have two more segments. Let's start with the leftmost. And this is -infinity to -11, which we see over here, we found it's below the x-axis. So this whole segment here needs to be below the x-axis. So just like this. And then finally, we have from 0 all the way until positive infinity, which we know is above the x-axis, which is why the graph will do precisely this. And yes, it is a lot of parts, and there will be quite a few like this. So I'm going to go through as many as my time allots, but that would conclude this problem. So now we're going to move on to a problem very similar to the previous problem. So we have a new rational function, and this one's a bit more elaborate than the previous one, so it'll give us a little bit more diversity with some of these parts. So we'll start off with the factored form. So remember, the factored form of a rational function is simply the factored form of the polynomial in the numerator and the polynomial in the denominator. So the numerator can be factored. In fact, both the numerator and the denominator can be factored. So that's what we're going to go ahead and represent our factored form as. So the numerator, so that will be, I'll go ahead and write that down. That's x plus 8 times x minus 7. So that's the numerator, x plus 8 times x minus 7. That's the factored form of this numerator. And the denominator is x minus 7 times x plus 2. So I'm going to go ahead and just conclude that that's the answer here. I'm hoping you're all comfortable with factorization by now. And some of you might look at this form and say, wait a minute, there's these two x minus 7s. Shouldn't we go ahead and cancel them? And so yes, but not now. As you know, my math lab is picky, so we're going to go ahead and leave it in this form, in this factored form, and we'll save that for lowest terms. So let's just leave it in that form for now, and we'll go to the domain. And remember, the domain for rational functions is, well, you set the denominator not equal to 0, that's why there's a not equal symbol right here, and you solve for x. Well, it turns out there are two values that we get. So we set the denominator not equal to 0, and we get two x values from this. We get positive 7, and we get negative 2. And that would represent our domain right there. So now when we get to lowest terms, so if we would have canceled that out, the x plus 7s, if we would have canceled that out in the beginning, we would have never seen that 7 was a domain restriction. Just because it cancels out doesn't mean we get rid of it in terms of the domain. However, we can simplify the problem now. So now lowest terms is saying, now if you have any cancellations, go ahead and do those. So what we had before, it was x plus 8, x minus 7. So I'm rewriting what's up here. X minus 7, x plus 2. And hopefully everybody sees that these x minus 7's cancel. And that simplifies really nicely down to x plus 8 divided by x plus 2. And that would represent your answer for part C here. And so, and now for the remainder of the problem, we only have to refer to this expression and not the original one. So the only thing that we had from here was that the domain also included the 7 that was canceled out. So now that we're looking at this, we can go ahead and figure out the x-intercepts and the y-intercepts, which, very similar to the last problem, we set y equal to 0. And so, as I mentioned in the previous video, this is the same thing as setting the numerator equal to 0, but if you don't remember that, then we set this expression here equal to 0. Clearing the denominator will result in the numerator being set equal to 0. And we get that x is negative 8, which means we would conclude negative 8 up here. So for the y-intercept says set x equal to 0. And so when we set both of these x's equal to 0, we simply get 8 divided by 2, which is just 4. So we get negative 8 for the x-intercept and 4 for the y-intercept. And now we move on to the behavior at any x-intercepts. So the behavior, remember, behavior is determined by, well, it's ultimately leading towards crossing and touching, which is determined by the multiplicity. So when we look at, well, if anything, what are the x-intercepts? Seems like we found one. That's x is equal to negative 8. So at x is equal to negative 8, and now we need to figure out whether the graph crosses or touches, which means we need to know the multiplicity. So it turns out, so remember, the negative 8 came from this expression here, or equivalently this expression. The factor from negative 8 is from this factor in the numerator, which has an exponent of 1, which means the multiplicity is 1. The multiplicity is 1, which is an odd number, which means that the graph crosses. And the graph crosses, I'll go ahead and just write down what I just said. The multiplicity is 1, which is an odd number. So that's the conclusion that we make based off of that information. And now we're going to move on to the vertical asymptotes, which is when things get a little bit different than what I've mentioned before. And there's only one exception, and I haven't mentioned it yet. So normally I've been saying the vertical asymptotes are very much in coordination with the domain. However, the vertical asymptotes in this case will not be 7 and negative 2. The reason why, so notice we had a cancellation. The x minus 7's canceled out. And when that happens, when a number cancels out like that, it means it no longer can be a vertical asymptote. Instead, and we'll see this at the end of this example, what we end up getting is a hole, an open circle, we get that on the graph. So what's 7, so 7's still a domain restriction, but because we canceled out the x minus 7 factor, that means that 7 is not a vertical asymptote. At x is 7, we'll just get an open circle on the graph. But -2 never got canceled out. Its factor is still there. So our vertical asymptote will be x is equal to -2, but not x is equal to 7. And the reason why is strictly because of that cancellation that happened. And so the behavior at the vertical asymptotes, that still corresponds in the same way. We figure out the multiplicity of -2, and from there we make the same observation as we did in part E. So here, at x is equal to -2 now, so x is equal to -2, the graph crosses by the same logic as this problem. So it will once again cross because the multiplicity is 1, which is an odd number. Is 1, which is odd. And finally, we move on to the horizontal asymptote. And remember, the horizontal asymptote, we have to compare the degree of the numerator and the denominator. Here, the degree of the numerator is 1. The degree of the denominator is also 1. So here we have that the degrees are the same. So the degrees are the same, which implies, so remember from the notes, this implies that our horizontal asymptote will be y is equal to the ratio of the leading coefficients. So ratio just means a fraction, so I'm going to anticipate a fraction of the leading coefficients. The leading coefficient in the numerator is an understood 1. It's a coefficient is the number in the very front, that's 1. In the denominator, the leading coefficient is 1. So technically it's 1 divided by 1, but we can simplify that to simply y is equal to 1. So technically we move on to part I, but again, that talks about the oblique asymptote, and I'm just telling you that it doesn't exist. So we'll move on to part J. And part J, it wants to know when the graph intersects the horizontal asymptote. Again, we don't worry about the oblique asymptotes. So we have to recall what the horizontal asymptote is. And in the problem, it was y is equal to 1. So the horizontal asymptote was y is equal to 1. So that implies, so what it does imply is we're setting the whole function equal to 1. So the whole function, remember, we can use that very nice simplified form. It was x plus 8 divided by x plus 2. And the reason why we have 1 here is simply because that was the horizontal asymptote. So we will have to work this one out a little bit, and it's actually going to have a weird conclusion to it. So if you multiply out the denominator, what you will end up getting is x plus 2 is equal to x plus 8. And you either get this from cross multiplication or multiplying both sides by the least common denominator. So 1 times x plus 2 is just x plus 2, and then x plus 8 after you clear out the denominator. So something to note here. So when you have a problem like this, say you would subtract x on both sides, you're going to end up noticing that the x cancels out on both sides. If you subtract x on both sides to get the like terms together, you're going to get that 2 is equal to 8. Now that, of course, doesn't make any sense. And in fact, that's okay that we hit something like this. We hit something that simply does not make any sense. So we were looking for when the graph intersects the horizontal asymptote, and we hit something that was clearly a contradiction. So what we conclude from that is that the graph simply does not. So the graph does not intersect the horizontal asymptote. And there will be an option to allow you to express this. So this is the conclusion. The graph does not intersect the horizontal asymptote. And so we'll go ahead and move on to part K over here, which again, as I mentioned in the previous problem, this is a very important sequence of steps. It also shows up in the next section, which means there's probably going to be a few of these on the upcoming test. And so we're trying to figure out where the graph is above and below the x-axis. And so, as I mentioned, there's this elaborate sequence of steps that we have to follow in order to determine this. So the first step being list all the domain restrictions in the x-intercepts. So we found those already. So the domain restrictions we found, this was in part B, that was 7 and -2. In the x-intercepts, we found those in part D. We found -8. So here we have 3 values in total. And so the second step I mentioned was to put these on a number line. In order, of course. So -8 is the smallest, -2 is next, and 7 comes last. So this is where I'm going to change up things a little bit from previously, because in the previous example I said there's 2 ways of going about this. One way would be, so the way I explained before was you would pick a test point from each segment, you would plug that into the original function, which is the x plus 8 over x plus 2 function, and a positive means you would put a plus sign, a negative means you'd put a minus sign. We're going to do it a little bit differently, just so I can show you both ways and you can pick whichever one you like more. So this step will be, you're only going to pick one test point. This one test point, so pick one test point, and this test point will be strictly larger than the list of values you gave. Just any number that's larger than all 3 of these. So 8. 8, you could pick 10, you could pick 100. It's just any point or any x value that's simply larger than all 3 of these. Larger than the numbers in part 1 up here. And so as I mentioned, we're going to pick 8. So 8, of course, larger than all of those. So from here, so now what we're going to do in step 4 is just, we're going to plug in 8 into the original function. So plug this number into the function. And again, so this part's going to seem very similar to before, but instead of a whole bunch of test points like we would have previously, we only have one test point. So it's the same exact idea though. The original function was x plus 8 divided by x plus 2. Now we're going to have 8 plus 8 divided by 8 plus 2. and we get a positive number from that. Again, remember, we don't care about the number itself. We care about the sign. But where does that positive go? So that positive, that plus sign, it ends up going after the 7 because it's greater than 7. So this segment is now what gets populated by that plus sign. So that plus sign's coming right here specifically to that segment because, of course, 8 is, well, larger than 7. So you might think, all right, cool. How does that help figure out the rest of these? And that's where the multiplicity comes into play. So step 5 will simply be somewhere on your number line, near each one of these numbers, jot down the multiplicity of that number. So here, for -8, the multiplicity, we already found this one. It was 1. And for -2, the multiplicity was 1. For 7, and again, this is coming from the fact that the factor for -8, the factor for it only has an exponent of 1. The factor for -2 comes from here, which has an exponent of 1. But 7 works a little bit differently in this problem. So technically 7 doesn't show up because we canceled it out. And if we look back at part A, so the factored form, if we look back at part A, so count how many times x minus 7 shows up in that problem, in that part. It happens once in the numerator and once in the denominator. Well, that's a multiplicity of 2. So just because we canceled it out, that doesn't mean that it goes away. It's insignificant. So instead, so in other words, any canceled out portions can be expected to have this sort of idea. So m equals 2, primarily because the part we canceled out, well, the part that we canceled out, it occurred twice, which means its multiplicity is 2. So that's something very important to notice if you decide to use this method. Again, you could pick test points. But the reason why this method is convenient is because this tells you crossing, crossing, and touching. So this is crossing, this is crossing, this is touching. And so the reason why that's helpful is because if you want to figure out any adjacent segments, so we know that this segment's positive. In order to go to this segment, we're crossing over something that's touching, which means that the sign will not alternate. That means that if we start off at somewhere that's a plus, and we come over here, this will also be a plus. Because touching does not alternate. Crossing alternates. So if we change segments from here to here, well then positive becomes a negative, because that's going over a crossing segment or number. And then same thing, -8 is crossing, which means the sign has to alternate. So that's one way of seeing people do a problem like this. And so I wanted to show you both methods, but either method leads up towards the construction of this number line with all of these segments. And so now, and again, yeah, part 5, I didn't write anything, but it's find the multiplicities of each number. And so what we can go ahead and do now is conclude this problem and then construct the graph. So what this problem concludes, so where are we above the x-axis? We're above the x-axis for any segments with a positive symbol. So that seems to be, well, this segment has a positive symbol. That's -infinity, to negative 8, negative infinity to negative 8. And remember, we're using a comma to separate answers. So where else has a positive symbol? This segment. Negative 2 to negative 2 to positive 7. And then one more. This segment, which is from 7 on to infinity. So that would be the answer for above the x-axis. Below the x-axis, it's simply, well, any segment that has a minus, which there's only one. That's negative 8 to negative 2. And so finally, after that, we can go ahead and generate the graph, given all of this information. So I'm actually going to go ahead and not do that. Try that again. Go over here and erase this. And we can use all of the given information to construct the graph. So I think this is part L. And we're simply constructing the graph at this point. And it seems to have bounds at 12 all over, negative 12, negative 12, positive 12, positive 12, and I think it goes in increments of 6. And so what we want to do is, well, use the ideas of the asymptotes as well as any characteristics associated with above and below to help determine the problem. So some of the asymptotes that we found, a vertical asymptote is that x is equal to negative 2. So if x is equal to negative 2, we'll call that about right here. And we know it goes up and down because this is a vertical asymptote. We found a horizontal asymptote at y equals 1. Horizontal means left to right. So this would go, we'll call it right here. And this alone will already help you narrow down, I think, 2, if not all the other graphs, because I think some of them one of them might have the vertical asymptote shifted over too much, or it might have this one in the wrong place in some regard. But let's keep going with this problem anyways. And so we also know that the graph is above the x-axis all the way over here on the left, as well as on the right to some regard. It seems like at negative 8, which is the x-intercept. So the x-intercept is over here, let's call it right here. So right there is the x-intercept of negative 8. And so we are above the x-axis from negative infinity all the way to negative 8. So notice that there's a little bit of room right here. And that's what describes that, because once it hits the x-intercept, then that's when it goes below the x-axis, which is, okay, we have a characterization for that. And it goes all the way to negative 2, which is what our asymptote represents. And then it goes on to be above the x-axis here and here. And the only reason why it's split up, remember, 7 is an open circle. So at around 7 here, there is an open circle. And that would be the motivation behind constructing this graph, and that would conclude this problem. So we're going to go ahead and look at an example that's similar to the other two. Since there's so many problems of this caliber throughout this homework, So we're going to look at a new rational function. This is, for example 3 in the notes, is the rational function 2x minus 6 divided by 9 minus x squared. And it's the same idea as before. We're going to start off with the factored form. So you might notice something about the initial form of this rational function. That is, the denominator is actually not in standard form. The denominator, well, standard form in general is descending exponent order. So we need to go ahead and fix the denominator in that regard before we continue. And that will help out with factoring. So negative x squared plus 9. All I did was rearrange the terms. So now the negative x squared is in front. And so now we additionally want to factor out the negative sign to get the leading term positive. And that is something we've done before in order to help with factoring, as we will see in a bit. So once we factor out the minus sign, now we can go ahead and factor the denominator here. So notice this is a difference of 2 squares. In particular, it is x plus 3, x minus 3. We can also go ahead and factor the numerator, because the numerator, both terms have a 2 in common. So let's go ahead and do that for the numerator. So that would be x minus 3, since distribution would verify that we proceeded correctly. And the denominator, the negative is still in front, but now x squared minus 9, as I mentioned, that's a difference of 2 squares. So now that is x plus 3, x minus 3. And this would be the factored form. And again, you might think, well, x minus 3 and x minus 3, couldn't we go ahead and cancel those? Well, not yet. Again, we'll leave that for the lowest terms part. And also we do this so we don't skip something with the domain. So the domain, as mentioned before, we set the denominator not equal to 0, and in particular, what we're going to get, so the denominator is exactly this. If we set that not equal to 0, well, the negative sign doesn't really matter here. Multiply both sides by -1. So that doesn't really matter, and all we're going to get is x minus 3 and x plus 3. So virtually the zeros of the denominator. You can look at it that way. So we get these two in the domain, but lowest terms, now what that wants us to do is to apply any cancellations, which we do have a cancellation. The x minus 3's cancel. And after we cancel those, we get -2 divided by x plus 3. So the x minus 3's canceled, and this minus sign, well, you can have a negative in the denominator and move it up to the numerator if it's multiplying. So it means the same exact thing. And so this would be, well, this will be our new function we get to look at throughout the remainder of these parts. So we'll move on to part D here, which is asking for the x-intercepts. So the x-intercepts, in general, what we do is set y equal to 0 and solve for x. So here, that same idea, set y equal to 0. And when we do that, so we're setting the whole function, the reduced function equal to 0. So now 0 is equal to -2 divided by x plus 3. And if you clear out the denominators like we've been doing, what that simplifies to is 0 is equal to -2. And as we found in the previous problem, or it might have been 2 problems ago, this is an expression that doesn't make sense, so we get no x-intercepts from this. We get no conclusion, so there are no x-intercepts that we get from this. The y-intercept, so we do get a y-intercept. Remember, y-intercept, we set x equal to 0. And when we set x equal to 0 here, pretty much that x disappears, and then we get -2 divided by 3. So here we just get -2 over 3. And that's after setting x equal to 0. So we move on to the behavior at the x-intercepts, but we don't have any x-intercepts. The x-intercepts do not exist. So there is a choice that says there are no x-intercepts. So we will go ahead and conclude with that. And that would be part E right there. The vertical asymptotes though. So in general, the vertical asymptotes in the domain are closely related, but it's not entirely forthcoming about what the vertical asymptotes are. In particular, there's a number can be in the domain restriction and not be a vertical asymptote, as we saw in the previous problem. And so in this problem right here, we see that after everything was reduced, the vertical asymptote is -3, as x is equal to -3. And the reason why +3 is not involved is because the factor corresponding to +3 canceled out. So again, whenever a factor cancels out, the corresponding number will not be a vertical asymptote. So notice the -3 number came from here, which did not factor out, or did not cancel out rather. And remember, if something cancels out, then it creates a hole in the graph. It's not an asymptote, it's a hole on the graph, which we'll see at the end of this problem when we graph everything. And then we look at the behavior at the vertical asymptotes. So that behavior will be, so we have to figure out the multiplicity. So the multiplicity of the x plus 3 factor, where the -3 came from, is 1. The factor only occurs once, there's no exponent with it, so multiplicity is 1. So the multiplicity is 1, which is odd. But remember, this is happening at asymptotes, not at an x-intercept. So crossing and touching doesn't make as much sense in this regard. Instead, it's how do the infinities alternate? Because these are at vertical asymptotes. A vertical asymptote, so verticals up and down. So things just simply do not cross and touch vertical asymptotes. Instead, they go towards positive infinity, or they go towards negative infinity. And the question is, on both sides of the vertical asymptote, how can we determine if one side goes towards infinity and the other one goes towards negative infinity, or do they both go towards positive infinity or both go towards negative infinity? Well, that comes down to crossing and touching. So this is the generalization. So since this is odd, that tells us, well, normally crossing, but that will tell us that one side will be positive infinity and one side will be negative infinity. So one side is positive infinity, other side must be alternating. So the other side must be alternating. And so now we're going to move on to part H, which is asking for the horizontal asymptotes. So the horizontal asymptote requires comparing the degrees of the numerator and the denominator. I went ahead and wrote down the simplified form up here. So if we look at that form up there, the degree of the numerator, so the degree of the numerator is, and you might notice in the numerator, it's just -2. So that's understood to have a degree of 0. There's no variable, so the degree is actually 0. And the degree of the denominator, well, in the denominator, it's just 1. There is a variable, but it only has a power of 1. So the degree of the denominator is larger, and because the degree of the denominator is larger, then we automatically get that the horizontal asymptote is y is equal to 0. It's just automatically 0. We get that one for free whenever the degree is larger in the denominator than in the numerator. So we would conclude part H with that. And so now we move on to where does the graph intersect the horizontal asymptote, if anywhere? So the horizontal asymptote is y equals 0. So that implies that we're setting the whole function equal to 0. And we actually did this already. So we've done this already. And the conclusion that we got, when you clear the denominator, you just get that 0 is equal to -2. And with this situation here, this just simply doesn't make any sense. So this doesn't make any sense, which means that the graph will not intersect the horizontal asymptote anywhere. There's no point of intersection. Or there will be an equivalent option on MyMathLab. And we move on to part K. So this is, again, similar to the other problems. Part K first requires us to make a list for finding the intervals above the x-axis and below the x-axis. So we're making a list, and this list will contain domain restrictions and x-intercepts. So domain restrictions and x-intercepts. So we didn't have any x-intercepts, so we figured that out in part D. In part B, we found two domain restrictions, +3 and -3. And it is okay that we are resurfacing a value that we canceled out in the beginning. It's still a domain restriction. That's why it's important to determine the domain before you simplify. And so, if you recall the directions from before, I had you all construct a number line and plot -3 and +3 on it. So I've shown you two different methods of how to do this. I'm going to stay consistent with the first method I used, but if you want to try the second method and verify it with the answer I conclude with, then yeah, try to mess around with that one and see how it goes. And so, as I mentioned, I'm going to do the former way, which means I have to pick test points from each segment. When I plotted these two, we came up with three segments here. So each segment, we're going to pick a test point from. So a test point, it's a temporary number that we're going to use to help us find some answer. So here we pick any number that's, well, the only criteria is that it's less than -3. So -4. -3 to 3, 0. Any number larger than 3, I'll pick +4. So that's step 3. Step 3 is picking the test points. And so now what we want to do is go ahead and plug each one of those into the original function to determine whether they give us a positive number or a negative number. So we'll go ahead and plug in x is equal to -4, the first one, and we plug that into the now simplified form. So it won't work out too horribly. And from this, it seems like we're going to get a positive number. It's positive because the denominator will give us a negative, and there's already a negative in the numerator, so we get a positive from -4, which corresponds to, so -4 gives us a positive. Now that we get that, -4 should be ignored. I just scratched it out. And so we move on to x equals 0. So that's -2 divided by 0 plus 3, and that gives us a negative number. In fact, it's just -2 over 3. So that's when we plugged in 0. So at 0, we now have a negative number, and we can scratch out 0. Finally, x is equal to 4. So once again, -2 divided by 4 plus 3, 4 plus 3, but in any case, we get another negative. So all the way on the far right here, we get a negative, and we can scratch out the 4. And now that we did all of that, we can go ahead and figure out the intervals that are above and below the x-axis. So I'll go ahead and add that over here. So intervals start off with above the x-axis. Well, that corresponds to any segment that has, well, a plus sign. So that segment is from -infinity to -3. And that's it. All the other ones have the minus notation. So we'll save those for the next part. And so, speaking of the next part, so intervals below the x-axis, we just go ahead and notate all of the ones with the negative notation. So this segment, which is -3 to +3, and comma, because we have another segment. It's this segment here, which is +3, so +3 all the way to +infinity. And so now that we have all of this information, we can go ahead and conclude with the graph of the function. So this is part L. And so let's see, with part L, it seems to have 10, 10, -10, -10 like that. Okay, and so we can start off by, well, plotting the asymptotes. So we got one vertical asymptote of x is equal to -3. So call that right about here. So x is equal to -3. That was the only one. We found a horizontal asymptote of 0. So that would be right on the x-axis. And now we can go ahead and use the intervals above and below to construct the graph. Since we know that the graph will very much align with the asymptotes, so from -infinity to -3, the interval will be above the x-axis. So from -infinity all the way to -3, this will all be above the x-axis. And again, these graphs generally converge or get really, really close to these asymptotes. So I have a pretty good understanding of how to sketch everything using the asymptotes as sort of a guide. And then here it says the intervals that are below the x-axis, it starts from -3 to +3. So here's the -3, and it keeps going. And then it goes all the way to where x is +3. And the reason why it just abruptly stops there, I mean, there's no asymptote there, so why? Well, the reason why is because since we canceled out that 3 factor earlier, we get an open circle. So I'm going to put an open circle here. An open circle. And then it says, all right, from the open circle, keep going. So if you're looking through the answer choices and wondering why this one has an open circle, that's the motivation why. And all of this would conclude this problem. We'll move on to example 4 from the notes. In example 4, it resembles a homework problem that will give you the graph of the function and ask you ultimately to determine which one of the functions would generate a graph like this. And so the first thing that I would have you all notice is, well, the denominators on these two are different than the denominators over here. Notice a plus and a minus. Well, it turns out this is actually a pretty big deal. So notice with the graph, we have two vertical asymptotes. One seems to be at x is equal to -4. So we have two vertical asymptotes. X is equal to -4 and +4. That's these two. So that means we need to have a function that also has those vertical asymptotes. But how do we find vertical asymptotes? Well, normally we set the denominator equal to 0. And you might notice, if we take any one of these two denominators and set either one of their denominators equal to 0, so what we would get, so x squared plus 16 is equal to 0, you're going to end up with a domain error. The reason why is when you go to solve, you will end up taking the square root of -16. That is something that we cannot do. So you cannot take the square root of a negative number. So you try to take the square root, but then this gives you an answer that, well, it gives you a result that cannot be processed. You get a domain error. So here, these two problems, what this reverts to saying is that these two problems do not have a vertical asymptote, because when you try to set their denominator equal to 0, you get no numbers, which means you would have no vertical asymptotes. So immediately, B and D are both out by that mere reason alone. And so we narrow it down to choices A and C. Now notice the only difference between choice A and choice C is this lingering negative sign, or lack thereof. And so in particular, now we need to use that to determine the horizontal asymptote. That will help us distinguish between the horizontal asymptote in this problem. So you might notice that the horizontal asymptote, so they give us -2 and -4, so we can kind of interpolate the fact that the horizontal asymptote, I'll go ahead and write it in black, the horizontal asymptote is y is equal to -3, which means when we find the horizontal asymptote of the correct function, its horizontal asymptote needs to be -3. And so if we look at the first choice, so remember, how do you find the vertical asymptote? You compare the degree of the numerator and the denominator, and depending on how those degrees compare, you do that particular process. Well, it turns out in both problems, the degree of the numerator is 2, so in both problems, the degree of the numerator is 2, the degree of the denominator is also 2. So in both problems, the degrees are the same. And when the degrees are the same, then you get that, the horizontal asymptote is y is equal to the ratio of the leading coefficients. So remember that, the ratio of the leading coefficients. So the leading coefficients here, 3, and remember I said ratio, so that means fraction, divided by 1. So this one has a horizontal asymptote of +3, but we said we needed a horizontal asymptote of -3. So we can immediately cancel this one out as well.
which leaves answer choice C. And just to verify that, well, same idea. The horizontal asymptote in this problem is y is equal to -3/1, which simplifies simply to -3. So it will, in both situations, for the vertical and the horizontal asymptote, it does match up with all the asymptotes on the graph. So we would conclude that answer choice C would be the corresponding function to this graph. Finally, for this section, we're going to look at one of the problems towards the end of the homework. And really the premise is just graph the function. And all they do is give you the function, and well, there's going to be 4 choices to choose from as for what the correct graph is. And 2 of them, not gonna lie, 2 of them are very, very similar looking. So I'm gonna talk through the motivation of this. And this process will also be helpful in the workbook problem that I assigned. So make sure you pay attention to the steps that I apply here. So this problem almost virtually breaks down to one of those 12-part problems that we've been doing. We're not going to look at it as intensely, but there's going to be a lot of overlapping components in that regard. And so we'll start off with, well, the factored form is nice. Let's go ahead and put this in a factored form right fast. So there's only one real thing to do here to get this into a factored form. And you might notice it's the denominator being a difference of 2 squares. So really the only thing to do here is factor it as such. And that will help us determine, well, characteristics about the domain and the vertical asymptote. There's no cancellations. We don't have to worry about any cancellations. So there's going to be no holes in the graph or anything. So we can go ahead and jump directly into the domain. And since we're not giving this in some special format, this is our scratch work off to the side. The domain, we find that whenever we set the denominator not equal to 0. So the denominator is in fact x plus 8 times x minus 8. And what we get from that is -8 and +8 for the domain. In particular, since there's no cancellations, these will also be representations of our vertical asymptote. Again, we're not being forced to input all of this information into MyMathLab, so we can organize it as we please. So we might as well go ahead and identify this as the vertical asymptote. In fact, there's two. There's 2 vertical asymptotes because we found 2 domain restrictions. In fact, I should probably notate this as x can't equal -8, +8. But the vertical asymptotes, since there's no cancellations, it just says set those equal to instead. And what that tells us is for our graph over here, we can slowly start to add things to it. So at -8, we'll call it about here. Remember, these are vertical asymptotes. In the graph, also the graph for all the multiple choices, they won't have x equals -8. They'll just have the minor ticks on the graph. And so also we have x is +8. So we can slowly, again, we could slowly start to add things to the graph. So let's go ahead and make some room here for the horizontal asymptote. So the horizontal asymptote that's simply comparing the degrees of the numerator and the denominator, and depending on how those degrees compare with each other, it gives us a different option. So here, Actually, this form does a better job of showing how the degrees compare. The degree of the numerator is 1, so I'll go ahead and write that down. The degree of the numerator is 1. The degree of the denominator is 2. Again, this one does a better job of expressing that because we can see that the largest exponent is 2. As for this one right here, which you would have to use term domination to ultimately get to. So with this here, the degree of the numerator is smaller than the degree of the denominator, so we get this one for free. It's just y is equal to 0. That's the one you get for free when the denominator degree is larger. So again, we can come over here to the graph and provide that information. So y is 0, that's a horizontal asymptote, so that tells you the orientation. It would be left to right. So we can add that, and we can move on to the intercepts. So with the intercepts, there's x-intercepts and y-intercepts. We'll start off with the x-intercepts, which remember, x-intercepts, you set y equal to 0 and solve for x. So when we set y equal to 0, we're setting the whole function equal to 0. Or another way you can think about this is your x-intercepts are when your numerator is set equal to 0. If you don't realize that immediately, that's okay. You end up getting to that step immediately after you clear out the denominator. Because once you clear out the denominator, well, you're multiplying the denominator to 0, which is always 0. And so now we get to this expression here. If we divide 7 on both sides, then all we get, that x is 0. So if anything, we know that the x-intercept here is x equals 0. So that tells us that the graph will cross right here on the origin. So the ordered pair is x is equal to 0, y is equal to 0. And so additionally, the y-intercept, we set x equal to 0. So when we set x equal to 0, we get a 0, so we get 7 times 0 divided by, well, it doesn't really matter. What does matter is the fact that 7 times 0 is 0, and we have 0 divided by stuff. So ultimately what I'm trying to say is that once you set x equal to 0, you'll end up getting that y is 0. So you'll get the same point back. So when x is 0, y is 0. So that just means we only have one intercept. And there it is right there. All right, so that tells us a little bit more about the graph. Now we can go ahead and look at the intervals above the axis and below the x-axis. So above, below x-axis. And this will tell us whether we draw our graphs here, 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 here. It tells us in what region will the graph be occurring at. So this is that elongated process. So the listing here, it seems like we found that -8, +8, and also 0. Because remember, the listing was the domain restrictions, we found 2 of them, as well as the x-intercepts, which we found 0. We can put these on the number line in order. So -8, then 0, then +8. We can go ahead and pick out test points from each one of those regions. So from here, -9, from here, -4, from here, +4, from here 9. Or you can use the methodology I explained in, I think, the second example. But we're gonna go ahead and plug each one of those into the original function here and figure out the sign that we get. Now, if you do this the other way, this is when that other method that I described in example 2 would be very beneficial here. So whenever you plug in x is equal to -9, you get 7, -9 divided by -9 plus 8, -9 minus 8. And so it seems like you get a negative number in the numerator, a negative and a negative. So that's the way I try to look at this. You can also just use a calculator. You put the whole numerator in the calculator, the whole denominator in the calculator, and just divide at the end. Or you could think about it as the numerator is negative, the denominator is going to be a negative times a negative, which is a positive. Whatever way you do it, you'll just get that the output is a negative number, which means that for -9, we get a negative here, and we could scratch out -9 because it was a test point. We do the same thing for -4, +4, and 9. So for -4, it's the same idea. 7 times -4 divided by -4 plus 8, -4 minus 8. That's negative divided by a positive times negative. This is going to give us a positive number, or whichever method you prefer to do this. The -4 is out. And since I'll kind of incorporate both methods here, you could plug in 4 and you'll end up getting a negative number. And the reason I know that so quickly is because the multiplicity of 0 here is 1. 1 is odd. Odd means crossing, which means the signs have to alternate when you go around 0. So that's one way you can look at it, or you could just plug 4 in, whichever way you prefer. And then same idea, you could plug 9 in, you'll get a positive number. Or you realize that the multiplicity of +8 is 1. The multiplicity is 1, which is an odd number, which tells you crossing, which means the signs have to alternate if you go around +8 here. Whichever way you do that, it doesn't matter. But now that we have all of the appropriate intervals labeled, we can go ahead and determine the intervals above and below. So we start off with the intervals above the x-axis. So this is above the x-axis, that would be all the ones with the plus signs. Seems to be this segment here, which is from -8 to 0. And a comma, because we have another segment. This segment over here, from +8 all the way to infinity. And then the intervals below. Well, it's just the opposite, all the ones with the negative. Negative infinity to -8. We'll start off with that one. So negative infinity to -8, and 0 to +8. So now we can use this to start to construct the graph. So negative infinity to -8 is this leftmost region. It says the interval must fall below. So that's why we will have a graph that does something along this line. That's below the x-axis, and the ends converge towards the asymptotes. From -8 to 0, so negative 8 to 0, so from that asymptote all the way to this intercept here, the interval is above, which we try to trace along the graph. We also want to hit the x-intercept, which would bring us right here. And that makes sense because once we hit the x-intercept, we cross, which is when we start to go below the x-axis. So that's another way of saying it just keeps going downwards like this. Finally, from 8 to infinity, that's when the interval is above the x-axis. So the graph always converges, or it gets really close to the asymptotes, and this would be, so aesthetically, this would be a very perfectly fine characterization for the graph of the function. For this problem though, as I mentioned, this one's a little tricky because there's two answer choices that look almost identical, or at least the example that this one's resembled off of. And that was the fact that their asymptotes, and they don't give you the dotted lines for this problem, their asymptotes, for one of them, it was at negative 8 and positive 8, which is good for our situation. They had another one where the asymptotes were at plus and minus 7. So on the graph, because the graphs are kind of squeezed in, it's very, very slightly compressed a little bit more. And that is something I want you all to be aware of, but upon being aware of that, this would be your final answer.